In this video, I will calculate part of structures of our boat. This is one of the videos where I had to figure out where to start and how to share 2 decades of experience. And structure is...
It's complicated.
When I start with new structural design, first step is to position bulkheads. Bulkheads are a very important part of the whole boat or ship design. They are used to make fire integrity of the boat, or better saying, to stop fire to propagate through the ship. They are used as a boundary of tanks and watertight compartments. That means that they can save the boat from sinking in case of damage. With Titanic that wasn't the case, but we learned something from that. Beside these safety functions, there are more functions of bulkheads related to structural design, but we will talk about that in some of future episodes. Now I will position the bulkheads. One is below the aft seat to be support for that. 2 are placed in the middle of the boat where we said that we will have a live well or storage area. And 1 meter from bow we have additional bulkhead that we can form forward compartment that will be used as a storage for anchor, fenders, ropes, whatever. Now the question is how we are going to calculate the thickness of the bulkhead. We have several ways to do that, from direct calculations to empirical formulas in some of the books. I will use ISO rules. As you can see, in 2020 rules were updated, but for structure made of metal, not so much changed. Since rules are expensive and you can find all the versions on the web, I will use as well all the versions from 2008. So, as you can see in the screen, that's a formula for thickness, but we have one major unknown, and that is pressure. If you scroll a little above in the rules, you can find a section where formulas for calculation of the pressure are. And as you can see in the rules, there are several sections with formulas for calculation of the pressure for different areas of sailing or motor yacht. Under chapter 8.3, we can find formulas for pressure calculation for watertight bulkheads, and this formula, as you can see, is very simple, and the only input is waterhead. As you can see on the picture, waterhead is 2/3 of bulkhead height. So let's fill in formulas in Excel. I'll create 4 sections for 4 separate bulkheads to calculate pressure, although we have just 2 bulkheads. Now some of you will say, Nico, we have 4 bulkheads. Wait, stop. Yeah, we have 4 bulkheads, but 2 are watertight bulkheads and 2 are forming tank or live well in our case. Pressure calculation is different for those 2 types of bulkheads. Let's fill in formula for tank bulkhead pressure calculation, and we will do same thing, 4 of them. And next step is to find dimensions, so let's open Rhino and measure it there. Collision bulkhead is the highest one, so I will first measure height there. And as you can see, we have almost 1200 millimeters of height, and that gives us roughly 5.4 kilonewton per square meter of pressure. Aft bulkhead is less loaded since we have openings on the seating position at approximately 0.6 meter. This gives us pressure of 2.8 kilonewton per square meter. Now let's calculate pressure for the tank bulkhead. They're very closed and not that different in dimensions, so I will calculate just for one, and we can apply that to second one as well. So with tank bulkhead it's a different story. Every tank should be outfitted with the aeration point to release pressure or let air in to prevent vacuum in the tank and prevent implosion. So I will take a height of the aeration point just below deck, but as you can see in the rules, minimal height of the aeration point above tank top is 2 meters. This will give us design head of 2.3, and with formula that is translated to 16.3 kilonewton per square meter. This was first step. Actually, in every structural calculation, the first step is to determine loads that are acting on our structure. Next step is to calculate thickness of the bulkhead. Let's first find formula. Chapter 10 is intended for plating scantling formulas. If you scroll through that, you will find chapter for metal plating under 10.3, and formula for thickness calculation you can find on 10.3.2. And as you can see, we need several parameters. All these parameters are described in the rules, and I will describe them in the glossary of the spreadsheet. Now let's add thickness calculation to our spreadsheet. Now we need to fill some parameters. Coefficients or formula to calculate coefficients are given in the rules. K2 is coefficient that consider length versus breadth of unsupported plate, while Kc is considering curvature of the plate or stiffener. Since our bulkheads are flat, Kc is always 1. Now let's look at parameter B. Figure 6 in rules provide definition of all these dimensions. B is defined as a short dimension of the panel between two closest stiffeners. This means that we need to assume where the stiffener will be. I will assume 500 mm for the start. Later on, when bottom structure is calculated, I will need to go back and align all the stiffeners from bottom, bulkhead and deck. But for now, we can continue like this. Now we have calculated the minimum required thickness of the plate. However, this thickness does not include any corrosion margin. Corrosion margin is addition to plate thickness that we add so that even if some thickness is gone due to the rust, both will still be safe and fulfill minimum needed requirements. At the same time, we are not able to buy plates in any thickness, and from production point of view, you don't want to go to very thin plates because they are going to distort due to the welding. I will add 0.6 mm for corrosion margin, and I will round up thickness to 3 mm. And I know that for some of you now that's too much and that you think that 2.5 is good enough and so on and so on, but trust me, from building point of view, you don't want to weld anything below 3 mm when it comes to boats. I mean, you can, but that depends what you want to achieve. If you want to achieve boat that is curvy, fine, but if you want to make a nice and smooth boat, you will have to put a lot of filler later on to smooth it, and there will be a lot of sanding and grinding, and I wouldn't go that direction. Now we need to choose aft bulkhead, and as you can see, it's way less loaded, and of course it should be less thick, and calculation is saying that it should be less thick, but I will still choose 3 mm, and there is a reason to it. I prefer to have plates with more or less similar thickness throughout whole boat when it comes to small boats, because it makes life easier, it makes less waste, less organization, less supply chain issues, and so on. So I will choose 3 mm steel plate for aft bulkhead as well, although it is overkill, I agree. We can also manipulate distance between stiffeners to get desired plate thickness. That's also something. And now when we have thickness, we can start calculation that will allow us to choose stiffeners for bulkheads. Formulas for stiffening members are in chapter 11. Formulas are calculating required shear area and section modulus. Let's type formulas in Excel. Coefficients we can find in table 16 and 17, and since we are working with the flat bulkheads, they are constant. When formulas are in, let's fill in data for each bulkhead. I will fill data for longest stiffener and calculate based on that. If this would be a racing boat, I would calculate each stiffener separately to save every gram of weight that is possible. But in our case, that is not needed. For forward bulkhead, length of stiffener is the same as the height of bulkhead. Distance between stiffeners is 500 mm, and we have required area and section modulus. For aft bulkhead, we have very short stiffener with length of just 260 mm and distance between stiffeners is 500. For tank bulkhead, we have length and distance between stiffeners of 500 mm rough. Now, when we have this required section modulus and required area, we need to choose what stiffener we will use. If you scroll a bit further in the rules, you can find several tables. The first table is defining what are limitations of dimensional proportions of stiffeners, and the other one is giving us section modulus for extruded profiles or flat bars. Let's search in the second table what stiffener satisfy our requirements, and it looks like we have an issue here. The minimum plate thickness in table is 4 mm, we have 3. And why is that an issue? Well, when you're calculating section modulus in a shear area of stiffener that is welded to or permanently attached to the plating, you need to take into account part of plate as well. So when we have a flat bar together with the dead plate forms actually a T-bar that section modulus is calculated for. That is why we need to calculate separately and we cannot use the table. At the same time, if you look at the rules, there is a prescribed how much of width of plate you should take into account when you are calculating section modulus. And in steel case, that's 80 thicknesses of material. So for our boat, that's 240. Since we have covered a lot in this episode in very short amount of time, I'm not going to bother you how to calculate section modulus. There are different ways how to calculate section modulus. There can be geometrical, you can make a calculation, you can just use 3D tool to give you that. But for now, I just created a new tab in a spreadsheet and I made a small tool that you can use for calculation of section modulus and shear area for flat bars and T-profiles. Now, as I said, first type in the plate thickness and width of plate that should be taken into account when we are calculating section modulus. And then I will change dimensions of profile until I don't find one that satisfies our needs. And how it looks like is that flat bar of 40 × 3 mm fits in our requirements. I will now fill in the chosen profile and calculated values of section module and area in main tab of the spreadsheet. And I will repeat that for other bulkheads. Next step is to model all this in 3D. And when it comes to 3D, I will create separate layers, one with the name of a plate thickness and the other one with the name of the profile. And I will store these created surfaces in those profiles. That's going to be immense help later on when we need to calculate the weight of the boat. So you see that I'm not using any 3D bodies, I'm using surfaces, and that's enough for this stage. The steps that we have taken here are the same for any type of boat or structure. Step 1 is determine load that are acting on our structure. Step 2 is determine thickness of plate. And step 3 is calculate shear area and section modulus and size the stiffener that fits that. I decided to give away this spreadsheet. You can find the link for download in the description below. And yeah, go and make one more step in design of your own boat. I will continue now with the calculation of rest of the structure. That means bottom, decks, transom, everything. And I will model all that in a 3D, and then we go to next step, and that's safety systems. See you next time.